your mind will genuinely struggle to grasp what we're about to describe. That's not a dramatic opening. It's simply the truth about a cosmic structure sitting more than 1 billion light-years away, drifting silently through the dark, home to more stars than any human mind can meaningfully picture. You probably feel like you already have a sense of how big space is. You've seen Earth looking like a marble next to Jupiter. You know the Sun could swallow 1 million Earths. You may even know that our Milky Way stretches across 100,000 light-years. But every mental comparison you've built up over your lifetime starts to crack when you encounter what astronomers found deep in the universe, far beyond anything familiar. Before we travel more than 1 billion light-years out, we need to start somewhere our minds can actually stand. Begin with Earth. Our planet feels enormous to us. Oceans stretch past the horizon. Continents take hours to fly across. Mountains climb kilometers into the sky. And yet, Earth is small. About 1.3 million Earths could fit inside the Sun. The Sun itself seems massive. It dominates our sky and holds nearly all the mass in our solar system, 99.8% of everything. Every planet, moon, asteroid, and comet answers to its gravity. But the Sun is just an average star. Some stars are so large that if one replaced our Sun, its surface would reach past the orbit of Mars. A few would swallow Jupiter entirely. Against those giants, our Sun is modest. But even stars are only the beginning. Our Sun is one of hundreds of billions of stars inside the Milky Way. That faint glowing band you see on a clear night, that's the combined light of distant suns, packed so tightly along the disk of our galaxy that they blur into a single glow. The Milky Way is about 100,000 light-years wide. Light travels at 186,000 miles every second. And even at that speed, crossing our galaxy takes 100,000 years. To feel the weight of that number, modern humans have existed for roughly 300,000 years. If a beam of light had started crossing the Milky Way when our earliest ancestors walked the Earth, it would only now be approaching the far edge. Our galaxy holds somewhere between 200 and 400 billion stars. Around many of them are planets. Around many of those planets are moons. The Milky Way is not empty space with a few scattered sparks. It is a vast, slowly rotating city of suns. And yet, enormous as it is, the Milky Way is not unusual. Just 2.5 million light-years away lies the Andromeda Galaxy. Slightly larger than ours, it may contain as many as 1 trillion stars. On a clear, dark night, you can see Andromeda with the naked eye. That tiny smudge in the sky is an entire galaxy, something most of human history didn't know. For a long time, people thought the Milky Way was the whole universe. Those hazy patches seen through early telescopes were assumed to be clouds within our own galaxy. Ancient cultures imagined the glowing band across the sky as spilled milk, a celestial river, or a road for departed souls. Then, in the early 20th century, astronomers realized those faint smudges weren't clouds at all. They were entire galaxies, island universes of their own. That discovery shattered our sense of scale completely. Suddenly, the universe wasn't one galaxy. It was billions. Today, astronomers estimate there may be as many as 2 trillion galaxies in the observable universe, each containing millions, billions, or even trillions of stars. And galaxies don't float randomly through space. They cluster together. Our Milky Way belongs to a small gathering called the Local Group, several dozen galaxies held together by gravity, drifting as a family. Groups gather into clusters. Clusters gather into superclusters. At the grandest scales, galaxies trace out enormous web-like filaments stretching across billions of light-years. If you could see the universe as a three-dimensional map galaxies would look like glowing beads strung along vast, invisible threads. This is the environment where giants are born. Most galaxies are modest in size. Many are dwarfs, containing only a few billion stars. Some are irregular, pulled and twisted by gravitational forces. Spiral galaxies like ours are common, with their graceful sweeping arms. Then there are elliptical galaxies, smooth, rounded systems filled mostly with older stars, lacking the dramatic structure of spirals. At the centers of the largest galaxy clusters, something remarkable unfolds. Gravity pulls everything inward. Imagine an invisible valley, with everything slowly rolling toward the lowest point. Over billions of years, galaxies drift toward that center. As they fall inward, escape becomes impossible. They collide, they merge, and the largest galaxies grow larger by absorbing the smaller ones. This process is slow beyond comprehension. A single galactic merger can take hundreds of millions of years. Two galaxies approach each other, stretch into long curving arcs, swing past, and slowly spiral together. Stars rarely collide during these events. The distances between them are too vast, but gravity reshapes everything. Gas clouds compress and trigger new star formation. Central black holes feed and blaze. Old structures are torn apart and rebuilt into something new. Over time, spiral arms are erased. Order becomes chaos. Chaos settles into something larger and smoother. This is how the most massive elliptical galaxies form, not in a single flash, but through layer upon layer of accumulated cosmic history. Our own galaxy is part of this process right now. The Milky Way is gradually pulling in smaller dwarf galaxies. Long arcs of stars stretch across our sky, the remnants of galaxies that came too close and were torn apart. And roughly 4 to 5 billion years from now, the Milky Way and Andromeda are expected to collide. Two vast spiral galaxies will merge and eventually settle into a single, larger elliptical system. This is not rare. It is the ordinary story of cosmic evolution. But sometimes, under the right conditions, this process goes much further. If a galaxy sits at the precise gravitational center of a rich cluster, it becomes the ultimate collector. Over billions of years, it absorbs galaxy after galaxy. Its halo expands, its stellar population swells, its central black hole grows with every merger. The universe builds from the bottom up. Small things merge into larger things, and larger things merge into giants. At the extreme end of this chain, far beyond galaxies like our own, far beyond even Andromeda, lies something that challenges our ability to visualize it at all. A galaxy not hundreds of thousands of light years across, but millions. A galaxy not containing hundreds of billions of stars, but tens of trillions. A galaxy sitting at the center of a massive cluster like a gravitational emperor, having spent billions of years consuming everything around it. Before we name it or try to measure it, pause. Everything we've described so far, the Sun, the Milky Way, Andromeda, galaxy clusters, already stretches human imagination to its edge. And yet, all of that is only the stepping stone. Because what comes next is not just another galaxy. It is the largest galaxy we have ever discovered. More than 1 billion light-years from Earth, in the direction of the constellation Virgo, lies a massive gathering of galaxies known as Abell 2029. Through a telescope, it appears as a crowded patch of faint light. Dozens of galaxies packed together, bound by gravity, slowly circling a shared center. And at that center sits something extraordinary. Astronomers know it as EC 1101, a name that gives no hint of its true nature. When it was first cataloged, it appeared as nothing more than a dim, fuzzy glow. There was no way to know that this faint smudge would turn out to be one of the largest galaxies ever found. This galaxy stretches between 4 and 6 million light-years from edge to edge. The Milky Way is about 100,000 light-years wide, and that already feels unimaginably large. But this giant is 40 to 60 times bigger in diameter. If our galaxy were shrunk to the size of a coin, this one would span the length of a large room. If it occupied the Milky Way's position in space, it wouldn't just swallow our galaxy. It would also engulf Andromeda. The entire local group, dozens of galaxies spread across millions of light-years, would fit inside its structure. And size is only the beginning. This galaxy is estimated to contain around 100 trillion stars. The Milky Way may hold a few hundred billion at most. That means this single galaxy could hold hundreds of times more stars than our entire home system. If you tried to count them at 1 star per second without ever stopping, it would take more than 3 million years to finish. 3 million years ago, our early human ancestors were just beginning to walk upright. And we're not even seeing this galaxy as it exists today. The light reaching our telescopes left those stars more than 1 billion years ago, long before complex life appeared on Earth. While evolution was slowly unfolding on our planet, those photons were crossing the vast emptiness between galaxies. This galaxy is not a spiral. It is an elliptical, smooth, rounded, lacking the elegant arms we associate with classic galaxy images. Its stars orbit in many directions rather than in a flat disk, giving it a uniform, featureless appearance. Elliptical galaxies are often ancient. Their hottest, brightest stars burned out long ago. What remains are older, cooler, redder stars, stellar elders that have been shining for billions of years. Despite its enormous size and staggering number of stars, this giant is relatively quiet. New stars form only rarely. The gas needed to fuel stellar birth has mostly been consumed or heated beyond usefulness. How did something this large form in the first place? The answer lies in its position. Sitting at the gravitational center of Abell 2029 gave this galaxy a powerful advantage. In clusters like this, gravity pulls smaller galaxies inward over billions of years. As they drift toward the center, escape becomes impossible. When a smaller galaxy ventures too close, it's slowly torn apart. Its stars are stripped away and added to the larger system. Its gas is absorbed. Its central black hole eventually merges with the larger one at the core. This process has likely repeated again and again. Over billions of years, dozens of major galaxies may have been consumed, along with countless smaller ones. Each merger added mass. Each collision erased structure. Each event contributed to the immense scale we observe today. Astronomers sometimes call this galactic cannibalism. It sounds violent, but it is simply gravity acting over enormous spans of time. With every merger, original spiral structure was destroyed. Stars were scattered into new orbits. Order dissolved into chaos, and chaos settled into a smooth, rounded form. What we see today is the end result of that long history. And there is something quietly surprising about it. For all its mass, for all its stars, this galaxy is not especially bright. Many of its stars are old and dim. There are few young blue stars to illuminate it. It is massive, but subdued. Like an ancient city long past its peak. Its period of rapid growth appears to be over. Most nearby galaxies have already been absorbed. The giant now sits in a kind of equilibrium, dominant, but aging. When astronomers study this object, they're not just measuring size, they're reading a record of cosmic history written in starlight. The ages of the stars, their chemical fingerprints, and their motions all reveal clues about past mergers and long-vanished galaxies. This galaxy is not a single unified creation. It is a structure assembled from the remnants of many galaxies that once existed independently. Their shapes are gone. Their names are gone. But their stars still shine as part of something larger. That is what makes this object so important. It represents the extreme end of what the universe can build using gravity, time, and matter. It shows us that galaxies are not fixed, permanent things. They grow, collide, and evolve. The Milky Way feels enormous when we think about it. But this giant forces us to widen our sense of scale once again. Because if the universe can build a galaxy millions of light years wide, containing 100 trillion stars, then our picture of what is possible is still incomplete. And we haven't even reached the most extreme part yet. At the very center of this immense structure lies something even more astonishing than the galaxy itself. Every large galaxy we know of contains a supermassive black hole at its core. Our own Milky Way hosts one called Sagittarius A star, weighing about 4 million times the mass of the Sun. That already sounds enormous. 4 million suns compressed into a region smaller than our solar system. But the black hole inside this galactic giant belongs to a completely different category. Astronomers estimate it may contain tens of billions of times the mass of the Sun, possibly between 40 and 100 billion solar masses. If Sagittarius A star were the size of a coin, this black hole would be a mountain. If placed at the center of our solar system, its event horizon, the point beyond which not even light can escape, would stretch far beyond the orbit of Pluto. Everything we consider our cosmic neighborhood would lie inside a boundary of no return. And yet black holes are not cosmic vacuum cleaners pulling in everything around them. Their gravity behaves like that of any other object with the same mass. If our Sun were replaced by a black hole of equal mass, Earth would continue orbiting almost exactly as it does now. The difference lies in density, an unimaginable amount of mass compressed into a tiny region where space and time themselves bend around it. The closer you approach, the stranger physics becomes. Near the event horizon, time slows down relative to distant observers. Light curves. Paths that once seemed straight begin to spiral inward. And inside that boundary, every possible direction leads toward the center. The black hole at the heart of this galaxy didn't begin that way. Like the galaxy itself, it grew over billions of years. Each time a smaller galaxy was absorbed, its own central black hole was drawn inward. Eventually, two black holes would begin orbiting each other, spiraling closer together, radiating energy in the form of gravitational waves, ripples in space-time itself. When they finally merged, the result was a single, more massive black hole. This process likely happened dozens of times. With each merger, the central black hole gained mass. With each feeding event, it grew more powerful. At certain points in its history, it was anything but quiet. When gas falls toward a supermassive black hole, it doesn't immediately disappear. Instead, it forms a rapidly spinning disk around the event horizon. Friction and magnetic forces heat this material to extreme temperatures, causing it to glow brighter than entire galaxies. In these active phases, black holes can launch enormous jets of high-energy particles into space at nearly the speed of light. Jets that can stretch for millions of light years, carving vast cavities into the surrounding gas of the cluster. Observations of the cluster around this galaxy show exactly those kinds of cavities. Huge bubbles in the hot gas, likely inflated by past outbursts from the central black hole. For a time, This must have been one of the most energetic objects in its entire region of the universe. But today, it appears calm. No brilliant quasar blazes at its center. No intense feeding frenzy. The easy supply of cold gas that fuels dramatic activity has been largely exhausted. The black hole still dominates gravitationally, but it rests in a quieter phase, like a volcano that once reshaped the landscape, now dormant but not gone. The relationship between a galaxy and its central black hole is not one-sided. They grow together. The mass of the black hole is closely tied to the mass of the galaxy's central bulge. When too much gas begins cooling and drifting inward, the black hole can heat it again through energetic outbursts, slowing new star formation. In this way, it acts almost like a thermostat, regulating the growth of its host galaxy. In a system as massive as this one, that feedback may be exactly why star formation has slowed so dramatically. And then there are gravitational waves. When supermassive black holes merge, they release unimaginable amounts of energy, not as light, but as ripples in space-time itself, traveling outward at the speed of light, stretching and compressing space as they pass. In 2015, scientists first detected gravitational waves from merging black holes. Those were stellar mass black holes, far smaller than the giants found in galaxy centers. Future space-based detectors may one day capture the gravitational waves from merging supermassive black holes, like the ones that built this cosmic giant. When that happens, we won't just see the universe, we'll listen to it. Billions of years ago, such mergers almost certainly occurred at the heart of this galaxy. Each collision would have been catastrophic on scales we can barely imagine. Yet from that violence came stability. From that chaos came structure. The black hole now sitting quietly at the center is the accumulated memory of those ancient events. And yet, even this monster is not eternal. According to quantum physics, black holes slowly lose energy through a process known as Hawking radiation. Over inconceivably long timescales, far longer than the current age of the universe, even supermassive black holes will eventually evaporate. For a black hole containing tens of billions of solar masses, this would take a number of years so large it defies meaningful comparison. Trillions upon trillions of years. But not forever. Even the most massive object in this galaxy has an ending written into the laws of physics. When we think about the scale of this galaxy, it's easy to focus on the stars. 100 trillion points of light spread across millions of light years. But what we see may represent only a small fraction of what truly gives this giant its mass. Most of it is invisible. Astronomers call it dark matter. Dark matter doesn't glow, it doesn't absorb light or reflect it. If you look directly at it, you would see nothing at all. And yet, without it, galaxies like this could not exist in their current form. The first clues came from motion. When scientists measured how fast stars orbit in galaxies, they expected those speeds to decrease with distance from the center, just as planets in our solar system move more slowly the farther they are from the sun. That's how gravity from visible matter should behave. But that's not what they found. Stars far from galactic centers move far faster than they should, fast enough that they should escape into space unless something unseen is providing extra gravity. That unseen mass is dark matter. In spiral galaxies like the Milky Way, dark matter makes up roughly 85 to 90% of the total mass. The stars, glowing gas, and dust we can see are just the surface details. The true structure is built on an invisible foundation. Now imagine scaling that up. If our galaxy already sits inside a massive halo of dark matter, then a galaxy 40 to 60 times larger must sit inside something far greater. This giant is embedded in a dark matter halo that may extend tens of millions of light years into space, far beyond its visible stars. The luminous galaxy we observe is only the bright core of a much larger, unseen structure. If you could somehow visualize dark matter, this galaxy would appear as a glowing knot within an enormous invisible mountain of mass. And that mountain connects to an even larger structure. The cluster surrounding it, Abell 2029, is itself wrapped in an enormous dark matter halo. Clusters are among the most massive gravitationally bound objects in the universe. Their dark matter scaffolding binds hundreds of galaxies together. The visible galaxies are like lanterns hanging from an invisible framework. This is how the universe builds on the largest scales. After the Big Bang, slight variations in density caused dark matter to clump together first. Ordinary matter, hydrogen and helium gas, fell into those gravitational wells. Stars ignited, galaxies formed, clusters assembled. Without dark matter, gravity from normal matter alone would not have been strong enough to build structures this large before cosmic expansion pulled everything apart. In other words, this massive galaxy exists because of something we cannot see and do not yet fully understand. Scientists have been searching for dark matter particles for decades. Underground detectors listen for faint collisions. Space telescopes search for indirect signals. Particle accelerators try to recreate conditions from the early universe. So far, dark matter has remained silent. We know it exists because of its gravitational fingerprints. But we don't know what it is made of. And so, when we measure the total mass of this galactic giant, we're working with two layers: the visible and the invisible. The visible layer is already staggering: 100 trillion stars across millions of light years. But the invisible layer may contain even more mass. Some estimates suggest the total mass of this system, including its dark matter halo, could reach hundreds of trillions of solar masses. That is not just a galaxy. That is a gravitational titan. Now step back even further. Galaxies don't float randomly in empty space. They trace out enormous filaments stretching across the observable universe. Between those filaments lie vast cosmic voids, regions nearly empty of galaxies. If you could zoom out far enough, the universe would resemble a three-dimensional spider web. Bright knots mark galaxy clusters, long strands connect them. Dark matter forms the threads. This galaxy sits at one of those knots. Over billions of years, matter flowed along invisible dark matter highways into this region. Smaller galaxies formed along those filaments and gradually drifted inward, feeding the central giant. The location was perfect for growth, like a valley at the meeting point of rivers. And because of that, this galaxy was able to accumulate more mass than almost any other known structure. This brings us to an important realization. The size of this galaxy is not random. It represents the upper limit of what the universe can construct under the current laws of physics. Gravity pulls matter together. Dark matter provides the scaffolding. Cosmic expansion pushes everything apart. Somewhere between those forces lies a balance. The existence of this galaxy tells us something profound. It shows us that the cosmos allows structures to grow to scales millions of light years across, but not infinitely large. And there is something humbling in that. When we think of scale, we tend to focus on what we can see. But the universe keeps reminding us that the visible is only a small fraction of reality. The stars we can observe are surface details sitting on something far deeper. This galaxy, with its trillions of suns, is supported by an invisible ocean of mass, an ocean we have not yet directly touched or fully understood. We can measure light that traveled for 1 billion years, We can calculate mass from orbital motion. We can simulate cosmic structure formation on supercomputers. And still, most of what holds the largest galaxy ever discovered together remains unseen. There is beauty in that mystery. It means discovery is not finished. This giant doesn't represent the end of understanding. It represents a frontier, a boundary between what we know and what we're still learning. When we talk about this galaxy, it's easy to focus only on its size. The millions of light years, the trillions of stars, the central black hole weighing billions of suns. But there is another dimension just as staggering as physical scale, and that is time. The light reaching our telescopes today began its journey more than 1 billion years ago. We're not seeing this galaxy as it exists now. We're seeing it as it was in Earth's distant past. 1 billion years ago, our planet looked nothing like it does today. There were no forests, no animals on land, no familiar ecosystems. Life was simple, mostly microscopic, confined to the oceans. While evolution slowly unfolded here, photons were leaving distant stars in that galaxy and beginning their journey across intergalactic space. They traveled through darkness at 186,000 miles per second, crossing unimaginable distances without slowing, without stopping, carrying a record of their origin. Only now have they arrived. In astronomy, distance and time are inseparable. The farther we look, the further back we see. Every distant galaxy is a preserved memory of the universe at an earlier stage. This giant system is a snapshot from a cosmic era long gone. And that raises a fascinating question. What does it look like today? Over the last 1 billion years, stars inside it have lived out their lives and died. Some may have collapsed into black holes. Perhaps another galaxy drifted inward and was absorbed. Perhaps the central black hole experienced new bursts of activity. We simply don't know, because that information hasn't reached us yet. Astronomy, in this way, is a form of cosmic archaeology. We reconstruct history from ancient light. Now consider the physical distance itself. A single light year is about 6 trillion miles. Multiply that by 1 billion, and you begin to approach the gulf separating us from this galaxy. Even our fastest spacecraft would be hopelessly inadequate for such a journey. Voyager 1, traveling at roughly 38,000 miles per hour, would take tens of thousands of years just to reach the nearest star. To cross our own galaxy at that speed would require billions of years. To cross this giant would take longer than the universe has existed. Even light, the fastest thing in existence, needs millions of years to travel from one side of it to the other. If there were civilizations living on opposite edges of this galaxy, a message sent at the speed of light would not arrive for several million years. A reply would take just as long to return. Communication across a single galaxy would unfold on geological timescales. This galaxy, despite its size, is not young. Most of its stars are ancient. The brilliant blue stars that burn quickly and die young have largely disappeared. Star formation has slowed dramatically because the cold gas required to create new stars has mostly been used up or heated beyond the point where it can collapse. Over the next tens of billions of years, its remaining sun-like stars will expand into red giants before shedding their outer layers and shrinking into white dwarfs. Smaller red dwarf stars, which burn their fuel slowly and efficiently, will continue shining for trillions of years, the last lights to remain long after brighter stars have faded. But even red dwarfs do not shine forever. Eventually, star formation across the universe will cease entirely. Gas will become too sparse to collapse into new suns. One by one, stars will exhaust their fuel. The galaxy will dim gradually, not in a dramatic collapse, but in a slow, quiet fading. What remains after that is a collection of stellar remnants: white dwarfs, neutron stars, and black holes drifting through a darkened structure. At the center, the supermassive black hole will persist far longer than any star. Yet even that colossal object is not eternal. Through Hawking radiation, over timescales so vast they barely fit into mathematics, it will eventually evaporate. Not soon, not in billions or trillions of years, but one day. The largest galaxy we've ever discovered will not last forever. It exists within a window of cosmic history, just as we do. There is something quietly profound in that realization. We live at a time when galaxies still glow brightly, when stars are abundant, when distant clusters are still visible across billions of light years. In the far future, cosmic expansion will carry many galaxies beyond the observable horizon. Observers living trillions of years from now might see only their immediate surroundings, unaware that a universe filled with trillions of galaxies once surrounded them. Right now, we are fortunate. We can look outward and see the universe in its richness. We can detect a galaxy millions of light years across and measure its properties with surprising precision. We can calculate its distance, estimate its mass, and reconstruct its past. And in doing so, we confront something extraordinary. Even the largest structures built by gravity are temporary. They are assembled slowly over billions of years. They shine for a time, then they fade. This giant galaxy is not just an object in space. It is a moment in the long unfolding story of the cosmos, a monument to what gravity can build, and a reminder that even monuments eventually erode. When we step back from the numbers, millions of light years, trillions of stars, billions of solar masses, we're left with something deeper than statistics. We're left with perspective. The largest galaxy we've discovered is not just a record-breaking object. It is a statement about what the universe is capable of. It is gravity given time. It is matter given patience. It is the slow, relentless assembly of structure across billions of years. And yet, despite its size, it follows the same rules as everything else. The same gravity that pulls an apple toward the ground shapes galaxies. The same atomic physics that powers our sun powers its stars. The same elements found in our bodies, carbon, oxygen, iron, exist in its distant suns. There is no special set of laws for the large and another for the small. The universe scales upward using the same blueprint. That realization changes how we see ourselves. When you hear that a galaxy contains 100 trillion stars, it's natural to feel small. Our planet becomes a dot. Our species becomes a brief flicker. Our lives, measured in decades, seem insignificant next to billions of years of cosmic evolution. But there is another way to look at it. The atoms in your body were forged inside stars. Long before Earth formed, earlier generations of stars fused hydrogen into heavier elements and scattered them through space in supernova explosions. Those elements eventually became part of a cloud of gas that collapsed to form our sun and planets. The same processes that built that distant giant also built you. The universe did not create galaxies and then separately create life. Life emerged from within galaxies. We are not outside observers of the cosmos. We are a product of it. When we look toward that enormous structure more than 1 billion light years away, we are looking at a distant relative, another expression of the same cosmic chemistry. And there is something even more remarkable. That galaxy doesn't know we exist. Its stars burn. Its black hole rests at the center. Its structure slowly evolves. It is indifferent to our presence, but we know it exists. On a small rocky planet orbiting an average star in an ordinary spiral galaxy, a species evolved the capacity to ask questions. We built telescopes. We developed physics. We learned how light travels and how gravity behaves. We decoded faint signals arriving from across intergalactic space. And from those signals, we reconstructed something enormous. That is extraordinary. In a universe filled mostly with dark matter and radiation, with empty space stretching between islands of stars, consciousness has emerged. Matter has arranged itself in such a way that it can reflect on its own origins. When we measure the size of the largest galaxy ever discovered, the universe is, in a sense, measuring itself. This perspective doesn't make us small. It connects us. The story of that galaxy is also the story of growth from below. Tiny fluctuations in the early universe grew into clumps of dark matter. Gas fell into those clumps. The first stars formed. Small galaxies merged into larger ones. Larger ones merged into giants. The same process that created that enormous elliptical galaxy shaped our Milky Way. And the same process will eventually merge the Milky Way with Andromeda. We are not spectators to cosmic evolution. We are participants within it. In that sense, the giant we've been discussing is not an alien phenomenon. It is an extreme version of something happening everywhere. It shows us the endpoint of accumulation. It reveals what happens when gravity is given enough time and enough material. But it also reveals limits. Galaxies don't grow forever. Cosmic expansion stretches space. Dark energy accelerates that expansion. Eventually, galaxy clusters become isolated islands. New material stops falling inward. Growth slows and stops. Even the largest galaxies reach a kind of final form. The existence of this giant tells us something profound about balance. Gravity pulls matter together. Cosmic expansion pushes it apart. Dark matter shapes the framework. Ordinary matter lights up the structure with stars. Somewhere within that balance lies the maximum size a galaxy can achieve. And we are fortunate enough to live in an era when we can see it. If intelligent beings exist within that galaxy, and we don't know if they do, their night sky would look completely different from ours. They would see a dense scattering of ancient stars in every direction. They might not see graceful spiral arms or a bright band crossing the sky. Their view of the cosmos would be shaped by their location inside a vast elliptical system. But perhaps they too would look outward. Perhaps they would detect other galaxy clusters in the distance. Perhaps they would measure the redshift of light and discover cosmic expansion. Perhaps they would ask the same questions we ask. How did this begin? How large is everything? What is our place within it? It's possible that somewhere among those 100 trillion stars, minds are wondering about the universe. And from their perspective, our Milky Way would be just another faint spiral among countless others. That symmetry is humbling. We're not at the center. We're not in the largest structure. We're in one galaxy among trillions, orbiting one star among hundreds of billions. And yet we are capable of understanding galaxies millions of light years across. That is not small. The largest galaxy ever discovered stretches imagination to its limit. But the capacity to imagine it, to measure it, to model it, to partially comprehend it, is equally astonishing. What makes that galaxy truly extraordinary is not only its size, it is what it reveals. It reveals that the universe is capable of building structures on scales that dwarf human intuition. It reveals that the same simple laws of physics can generate astonishing complexity. and it reveals that we live in a brief, luminous chapter of cosmic history, when such structures still shine brightly enough to be seen. One day, far in the future, galaxies will fade, stars will burn out, the universe will grow darker and quieter. But right now, in this moment, we can look out and see giants. And in seeing them, we expand not just our knowledge, but our sense of belonging in something far larger than ourselves. The biggest galaxy ever discovered is larger than imagination. But the fact that imagination can reach that far, that may be the most remarkable discovery of all. Your mind will genuinely struggle to grasp what we're about to describe. That's not a dramatic opening. It's simply the truth about a cosmic structure sitting more than 1 billion light years away.